So that is a contradiction proof. So now we did one contrapositive proof and one contradiction proof. Let's go back to contrapositive. Just to shake things up, we're just going to do some examples, get some muscle memory here. So let's try to prove the claim. And this is the one I attempted last time, but I had it all complicated, more complicated than it needed to be. Here's the claim. I'm just going to write it in the math formal way. For all P in our set of primes, and for all A in Z, and for all B in Z, P not dividing A and P not dividing B implies P does not divide AB. Now, this is kind of a mouthful, right? What this is saying is that if you have two numbers, A and B, and P is a prime, if P doesn't divide A and it doesn't divide B, it can't divide their multiple, their product, which is kind of weird, by the way. Because I mean, let's think about it. For example, 10 does not divide 6, and 10 does not divide, let's say 5, right? But 10 does divide 30, which equals 5 times 6, right? So just because 10 didn't divide both of those doesn't mean it doesn't divide the product. But 10's not prime. What I'm saying is that for any prime number, if P doesn't divide the first one, or P doesn't divide the second one, it won't divide the product. That's interesting. And this sounds benign, but it's actually one of the fundamental parts of primes and is used in a bunch of high-level math, abstract algebra. It's pretty crazy. Anyway, let's do a side. First of all, do we think it's true or false? Let's kind of, like, one way to go about it is let's kind of try on our own to kind of prove it false. Like, what do you guys want to try? And actually, while you're thinking about that, here's a time where I will mention an important fact that we need for this problem, and that is the fundamental theorem of arithmetic. What that says is that every natural number, actually, so we could, it's the same principle, but it's a little more complicated with negative numbers. Let's just say this. For every natural number can be written uniquely as the product of primes. In this unique business, it's uniquely up to order. So what that's saying is that 24, for example, equals 2 cubed times 3. Or you can write 2 times 2 times 2 times 3. Right? So it's the product of primes. It also equals, and this is unique, it also equals 2 times 3 times 2 times 2. So you can switch around the order of the primes, but the point is they're all going to be there in the same numbers. We went over that before. So, how do we prove this? Well, if we try to go directly, we're going to have a hard time. Because P not dividing A, what that means is that there doesn't exist an integer. This means there does not exist an integer such that A equals PK. But this is like a negative. We're not saying A equals PK. Like, it's really nice. Like, this is like the foothold thing I'm talking about, right? It'd be really nice if we had this, but we're actually saying there doesn't exist an integer for this to happen. So we don't really know anything. We know this can't happen, but that's kind of, we're not saying much. Like, anything else could happen but this. That's like how do you work with that? So here's a bright idea.
I mean, I think we should use the contrapositive. I don't know why, but
I think that's a fantastic idea. Well, Benet, you remind me of me. Good job. Good job. Yes, Benet is very clever. And also maybe the only one willing to talk. And that is, we should use the contrapositive. Because if we look at the contrapositive of this, which remember is equivalent to the original statement, the contrapositive is, says, for all P, I'm going to go over this part, blah, blah, that the contrapositive of this conditional is that P divides AB implies that we don't have this. So the contrapositive, right, you take the negation of this, implies the negation of this. So the negation of P doesn't imply AB is that, well, P does imply AB, or divides, P does divide AB. And then this will imply the negation of P doesn't divide A and P doesn't divide B. But by De Morgan's law, right, this is saying that P divides AB implies that P divides A or P divides B. Right? Just distribute that negation and flip the into an OR. This is much better. This is so much better because now we get to assume, now we should have proved this. We can assume the hypothesis. So we get to assume that P divides AB. And since P divides AB, we know there exists a K such that PK equals AB. And that's huge, right? Now we actually have an equality we can play with. If we have an inequality, you know, you can't really do anything with that. Does that make sense? Why the contradiction is the same as this and why that might help? Okay, then. So let's work on this, right? First of all, notice that by the fundamental theorem of arithmetic, each of these guys has a unique prime decomposition, meaning a unique way to write them as a product of primes. So I'm going to say, let's go ahead and let K equal, let's just call it P1 all the way out to PT. That'll be K. And this is K's prime decomposition. And then A, that's going to equal Q1 out to QS, where all the Q's here are primes. Like, we just know that this does happen. Since A and K are natural numbers, right? Like, we can write them as a product of primes. And then same thing with B. Let's say R1 out to, we need some last index. Let's just say M. R1 out to RM. This is B's prime decomposition. We know these have to exist. But then if we substitute them into this formula here, we get P times P1 out to PT equals R1 out to RM times, oh no, E equals Q1 times Qn times R1 times Rm. This is the prime decomposition of the left side. This is the prime decomposition of the right side. Now, what does the fundamental theorem of arithmetic tell us about these two prime decompositions? Oh, oh wait, we just did Prime Day? Is that like Amazon Prime Day? That would have been good. Would have been good. Where do you think I got my knickknacks from? Those growing trees. Yeah, actually, nothing more knickknacks is wood. So yeah, they don't grow on trees. Yeah. The fundamental theorem of arithmetic says that every natural number can be written uniquely as a product of primes. And since PK and AB equal each other, PK and AB are the same number. Are the same number. And since PK and AB are the same number, they have the same prime decomposition. Up to ordering, right? It's unique. So that means this prime decomposition is the same as this prime decomposition. Let me give you an example, right? For example, 3 divides, let's say 45. Or 3 divides 10 times, yeah, 10 times 9, let's say. Right? So that means that there's some k such that 3k equals 10 times 9. And that k, we just know 10 times 9 is 90, so that k is 30. And now let's break down these prime decompositions here. So 3 is already prime, so its prime decomposition is itself. But 30, that breaks down into what? 2 times 15? But 2 times 15 is 3 times 5? And this breaks into 2 times 5 for 10, and 3 times 3 for 9. Notice, these are the exact same prime decomposition, just in a different order, but they're the same, right? Like the same numbers are there. And that's not a coincidence. That always happens for any of this stuff because of what we just talked about. Now, here's the big thing to notice, right? If the prime decompositions are the same, that means that P that's in the prime decomposition on the left side must be in the prime decomposition on the right side. It's got to be over here. In our case, in this example, 3 is over here. It's got to be. If it's not, if P doesn't show up over here, well, that means that this prime decomposition is different from this prime decomposition. We know that can't be true because prime decompositions are unique. Is this making sense? So that means that P has got to equal QI for one of these I's, or it's got to equal RJ for one of these J's, or for one of these guys. It's got to be one of these. It's got to be in here or here. But if it's one of the QIs, well, remember, A equals that. So that means P divides A. Or if it's one of the R's, well, B equals the multiplication of the R's. So that means P's in here somewhere. So P would divide B. So P's got to divide A or B. Hit me with questions. I felt really soulful the way I asked that. That was very nice, very peaceful. No questions? Are you sure? Does that make this make sense, or does that mean you don't even know where to start? I hope it's the first one. Okay, so let's think positive thoughts and get to the formal proof. So there's kind of two things going on here. I kind of combined two lessons in one. Number one, contradiction made things easier. Why did contradiction make things easier? It gave us this foothold. Rather than assuming that P does not divide A and P does not divide B, something that it's just hard to get your hands on. It tells us we can flip it and we can do the contrapositive part of it, which gives P divides AB implies this. That's much better. That gives us something that we can actually work with down here. That's the contradiction part. If you get that, you understand contradiction. It's good. The rest of this was some practice with our fundamental theorem of arithmetic. And it all comes down to the fact that, that every number can be broken down to primes uniquely.